Mina, you can get
Okay,
started.
I see the recording indicator. I didn't hear anything, but I'll get started.
We can hear you. It's all set up. Go for it.
Great. So thanks, Jacob, for the invitation. And thanks, Eric, for your talk. This is going to be a totally different direction. I'll be talking about the physics of black hole images, and we can learn from them. So in this I hope to illuminate the images of black holes a little bit. This is based on work that was originally published about a year ago now, but there's lots of interesting implications that I'm actively thinking about, and several other people are actively thinking about, and the EHT collaboration is thinking about as we look forward to higher resolution images of black holes in the future. So the motivation for this talk is this image that's shown on the first slide, and it's a picture of the supermassive black hole at the center of the Messier 87 galaxy, and it's dubbed M87 star. And before going on, I just want to thank the Event Horizon Telescope collaboration. This is a picture from the 2020 collaboration meeting that was in December. And the Event Horizon Telescope is an array of radio telescopes around the world, and it's made up of members that include hundreds of scientists from dozens of institutions worldwide. And without all of their hard work, this picture that we have of the black hole that came out in April of 2019 wouldn't have been possible, and many future, hopefully, images of black holes wouldn't be possible. So thanks to the EHT collaboration. And thanks to the EHT, we can now take pictures of black holes. And this immediately raises the questions of what do these pictures show us and what can we learn from them? And that will be the focus of my talk. So before going on, I just wanted to include this animation that shows how cool it is that we can go in to the Virgo galaxy, or the Virgo constellation, sorry, and we can travel through 53 million light years of space using the Event Horizon Telescope to the center of the Messier 87 galaxy, which we're zooming in on here. And there's a relativistic jet, there's a jet of matter traveling at relativistic speeds shooting out of the center of the galaxy. And we think that this jet is being powered by a supermassive black hole that sits at the center of the galaxy. And this supermassive black hole is what we've taken a picture of now for the first time. And so this is our very first picture of a black hole. It was released, again, as I said, in April of 2019. And what you can see is that there's a central dark patch in the center. That's where the black hole is. And it's surrounded by this ring of light with an asymmetric brightness profile. And so this is our very first picture, so it's a little bit blurry, but we think that we'll be able to take high resolution pictures soon. And when we do that, we think the higher resolution pictures will look like this, which is a simulation. But what's striking about it is that the ring of light, a higher resolution, we think will actually be very thin. And if you look closer to the edge of the dark shadow in the middle, there's actually an even thinner, even brighter ring. And we think that as we go to higher and higher resolution, we'll continue to see this series of increasingly thinner, increasingly brighter subrings piling up at the edge of the shadow. And this feature of the series of this brightness enhancement near the edge of the shadow isn't just seen in this particular simulation of M87, it's seen in many different simulations of many different images of black holes. And so it seems to be universal in simulations, and we think it is a universal feature of GR, which we've shown. So, the presence of this series of rings of light has been dubbed the black hole's photon ring, and some questions about it that we can immediately ask are, how do we describe the photon ring with general relativity? How can we measure it with high resolution using the Event Horizon Telescope? And what can we learn from it? So there's been a lot of work on this over the past year, and that's ongoing. And I'm only going to describe a couple aspects of it here. The first is that this photon ring consists of a series of exponentially narrow subrings. And second, that the polarization of the subrings encodes the black hole's spin. And what's important is that these are universal effects of general relativity in the sense that they don't depend on what astrophysical matter is surrounding the black hole or where it sits in space-time. We will see this series of subrings for any black hole surrounded by any type of matter or relatively generic accretion flow. And for how we can measure it with high resolution, we think this will be possible soon with the future extension of the Event Horizon Telescope to space. And most importantly, what can we learn from it? Well, we can hope to make a precise test of general relativity in the strong fields around a black hole. So experiments like LIGO or like gravitational redshift are measuring GR in weak gravitational fields and testing general relativity in the strong fields around black holes can point the way to new fundamental physics. And second, making a precise observation of the photon subrings can lead to a precise observation of black holes, the black hole's mass and spin, which I'll describe later in the talk. And this is interesting not only as a test of general relativity, but also for astrophysics, because we don't actually have a precise way yet to measure black hole spin. So this measurement could be done for the first time. And the spin of a black hole tells us lots of other interesting things about how the spin's related to the accretion flow, to this jet that's shooting out of it, and the magnetic fields around the black hole, et cetera. So there's lots of interesting stuff we can learn, and the rest of the talk will be answering these questions. So I'll be starting with some background, which probably everyone here is familiar with, but I think it's just nice to do a little review. That will talk about black holes and the black hole shadow. Then I'll review the subring structure of the photon ring and explain how it comes about. And then talk about how the subring polarization encodes spin. And then finally, how we can actually measure these features with the EHT in the future. So with that, I'll start with some background about how we observe black holes and what the black hole shadow is. And I thought it'd be nice to do just a little review of black holes that probably is some history of black holes, which is probably familiar to everyone here, but I wanted to emphasize how black holes have gone from sort of a mathematical curiosity to experimental reality over their history. So as we all know, they're a feature of Einstein's general relativity, discovered in 1915, and the first solution was by Schwarzschild, who showed that there was a Schwarzschild radius at which there's an event horizon of r equals 2 times g, which is Newton's constant times the mass of the black hole. And in 1931, Chandrasekhar showed that there's a limit to the maximum mass of white dwarf stars where the pressure can withstand the gravitational attraction of the star. And beyond this limiting mass, the star can collapse to something more dense, which could be dense enough to form a black hole. So with this idea, black holes can be something that are naturally an endpoint of an astrophysical process and not just a mathematical curiosity. And then briefly, the last name I'll mention is that of Roy Kerr, who gave a solution in general relativity. It's extremely non-trivial Kerr solution for spinning spherically symmetric black holes. And I mostly just wanted to include this really nice quote from Chandrasekhar, who said that upon learning about the Kerr solution, that in my entire scientific life, the most shattering experience has been the realization that an exact solution of Einstein's equations of general relativity provides the absolutely exact representation of untold numbers of massive black holes that populate the universe. So the Kerr solution gives us something that we can go out and test on the astrophysical black holes that we see, which are generically spinning. And then we can use our predictions from general relativity for tests in the Event Horizon Telescope. And I just wanted to review a little bit about ways to see black holes. Obviously, black holes are black, and so light doesn't come out of them, and we have to observe them indirectly. And so things like LIGO observe gravitational waves. Another way to observe a black hole is to infer its presence from stellar orbits. And this is an animation from Andrea Ghez' group in UCLA. She was one of the winners of the Nobel Prize. And this pictures of stars orbiting some unseen central object at the center of our galaxy. And they form these perfect Keplerian orbits. And we think that they orbit around this unseen center of mass, that's the black hole Sagittarius A star. So another way to see black holes indirectly, in addition to viewing the stellar orbits, is to look at the shadow that it casts. So since black holes curve space-time, light that's coming around light that's in the accretion disk around the black hole gets bent and lensed by the black hole. And the black hole will appear to cast a shadow on the light that is seen by a distant observer. So this screen here is supposed to be the sky of a distant observer. And when light comes from around the black hole, it appears to cast a shadow. All right. So the first person to calculate the shadow shape precisely was James Bardeen in 1973. And back in 1973, there was no really hope of observing it. And so he said, it's conceptually interesting, if not astrophysically very important, to calculate the precise apparent shape of the black hole. Unfortunately, there seems to be no hope of observing this effect. And it's a testament to our experimental advances now that this precise shadow shape is exactly what we are trying to see with the future extension of the EHT. Okay. So what we've seen so far is the supermassive black hole M87 star, and the size of the black hole shadow depends on the mass of the black hole. And so since M87 star is about 10 to the 9th solar masses, the size of the shadow is about 10 times that of our solar system, which is illustrated by this XKCD cartoon. And we can use the shadow to compare to our mass measurements from stellar dynamics. So from looking at the orbits of stars around M87 star, like that animation that I showed, we can estimate that the black hole mass is about 6.6 times 10 to the 9th solar masses. And the size of the shadow, which is observed for M87 star, exactly matches the shadow, or to this resolution, matches the shadow size predicted for a spinning black hole, which is about 5 times Newton's constant times the mass of the black hole. So far, this is consistent with what we expect for a Kerr black hole. And of course, as we go to higher resolution, we'll be able to measure this shadow size and shape more precisely and make a better comparison with general relativity. So when we do go to higher resolution, what we expect to see is this subring structure. And I'll go into what makes that up in general relativity. And as part of this, I'll answer the questions of what makes up the black hole image and how we can describe it quantitatively. So to think about the black hole image, it's useful first to think about, instead of light coming from the black hole, from around the black hole toward us, to think about shooting light backward from us into the geometry around the black hole. So here we're viewing the observer screen in the black hole from the side. And we can imagine shooting some light ray back. If we go very far away from, if we shoot it back very far away from the black hole, the light doesn't really feel any effect and travels basically in a straight line. And as we shoot light closer to the black hole, they'll be lensed and bent. And if we shoot light back at a precise distance, it will be trapped on a bound orbit around the black hole. And this is very important, that black holes are the only objects that we know of that can trap light in bound orbits around them. So this light could become trapped in a bound orbit, and anything closer than that will just fall in. So shooting straight back will just go in. Now, we can also think about the observer's screen from face on, and we can set up, or this is like the observer's screen or the observer's sky, and we can set up Cartesian coordinate systems on our image. This is just like X and Y, but following Bardeen, we're going to call it alpha and beta. And we can ask, when we look at this image, where are the points at which, when we shoot a light ray back, it will become trapped in a bound orbit around the black hole. And the set of such points actually forms a curve on the screen called the critical curve by Bardeen. And there's actually a range of radii at which photons can be trapped on bound orbits in the Kerr geometry. And so this curve is parameterized by radius, which is a cool thing. So converse, I guess, yeah, here, this is just what I said. It's called the critical curve. And if we think about it now from the bound orbits around the black hole, we can imagine perturbing them slightly. So the photon orbits in Kerr are unstable. So if we perturb a photon slightly, it'll either become unbound, orbit many times, and escape to us to be observed, or it will orbit many times and then fall into the black hole, never to be seen. And so because the set of bound orbits in this critical curve delineates between the photons that will escape to reach us and the ones that will fall into the black hole, it defines the edge of the black hole shadow. And when we think about light that reaches us, we can label it by the number of half orbits, n, that it makes around the black hole before it comes to us. And the reason why we care about half orbits instead of full orbits will become clear later in the talk. So this is another great animation that shows the light executing different number of half orbits that reaches us. So most of the light coming from around the black hole is just direct emission. So it undergoes n equals 0 half orbits and comes straight to us. But there's also light that executes n equals 1 half orbit. And because it has a longer path of travel around the black hole, it gets lensed and focused into this narrower region, and it will appear as a narrower, brighter ring on the screen. Then there's also light that executes n equals 2 half orbits or 1 full orbit, and it will be further focused into this narrower and brighter thin ring on the screen. So the light that we see when we take a picture comes from the sum of all of these arbitrary n number of half orbits. And that's what will make up what we see. I think, yeah, just as a reiteration here, the full image is made up of the sum of different sub-images that execute different that correspond to photons executing different number of half orbits. So this has sort of been a qualitative picture so far, but it can be described quantitatively in general relativity, just solving for the photon geodesics. And if we introduce a parameter d that describes the distance to the critical curve on the screen, and a number n that describes the number of half orbits that the photon executes, we can think about the width of the image that corresponds to the nth subring, or the photons that executes n half orbits. And what we find is that the width of the photon ring corresponding to the n+1 photons that execute n+1 half orbits is exponentially narrow compared to that of the image of the photons that undergo n half orbits. And what this means is that the width of the subrings corresponding to the different number of n half orbits goes to 0 as n goes to infinity. So they'll become exponentially narrow and close to this critical curve, which is outlined in black on the picture here. And so then all the subrings will sit on top of each other on the critical curve. And what's also important to note is that this exponential factor gamma is only a function of the black hole's mass and spin. It doesn't depend on anything about what the width of delta D0 or the direct image actually looks like. Once you know what that is, you can use the exponential magnification based on just the black hole's mass and spin to see what the width of the nth subring will look like. And so in this sense, the exponential narrowing is a universal feature of general relativity that's independent of the details of emission around the black hole. And what it also means, the fact that these width of the subrings goes to 0, is that all the photons are arriving at the same position, essentially, for large n. They're all arriving at the critical curve. And so they're all arriving at us with the same momentum, which means that they pass the same way through the matter near the black hole, which means that they pick up the same contributions to their intensity as they pass through the matter. And that's what this equation is showing, that for large n, the intensity of the n+1th, the intensity that corresponds to the n+1th image will be the same as that of the nth image, except for it'll appear at this exponentially narrowed distance dn+1. And what this is saying is that the images in intensity of the photon ring are self-similar. So, and they're given by this, and the self-similarity is given by a scaling controlled by this critical exponent. You can think of it as critical exponent gamma. And it's really cool that we see this symmetry, or we hope to see the symmetry in the sky around black holes. Now, I've mentioned, again, these are squiggly lines, so it's supposed to be at large n, but what's amazing is that the large n approximation is actually good for n greater than or equal to about 1. So we don't need to go to crazy high n in our observations to see this. We can just look at maybe n equals 2 and 3 and try to extract some of these universal features. So, and because this gamma only depends on mass and spin, if we can measure it, then this could give a precise way of measuring the mass and spin of the black hole. So just to emphasize that this subring structure is a feature of GR, and it's also been seen in high resolution simulations. So we're hoping that we can see it in data soon. But in the simulation, we can look at the intensity along different cross sections of this image that I showed before. So this plot on the right is showing the cross-sectional intensity as we move up along the blue line. That's left to right on this picture. And as we move from left to right on the red line, it's shown in red on this picture. And if we zoom in on a region that's close to the critical curve, we see that in the intensity, there's this piling up of sub-images, and they all have the same profile, but they're just squished exponentially close to the critical curve. And so we see this layered structure, and that will give rise to a logarithmic divergence in the brightness of the critical curve. All right, so that's going to be the end of my review of the subrings. And now I'll talk about how the subring polarization encodes spin, which is really interesting, and it'll involve answering the questions of how we describe polarization in the Kerr spacetime, and how polarized light appears to the observer and how it depends on spin. So polarization in Kerr has some very special properties. Just as a reminder, the Kerr black hole spin is labeled by a parameter A that ranges between 0 and 1, and we're going to be observing a black hole at this angle theta O for theta observer relative to the spin axis, which is shown with the red arrow. So photons, as usual, we'll give them a momentum P and a linear polarization that I'll call F. And the polarization is orthogonal to the photon's momentum and is parallel transported along its trajectory. So it obeys a parallel transport equation. And the symmetries of Kerr of stationarity and axisymmetry imply that the photon's trajectory has a conserved energy and a conserved angular momentum along the spin axis theta, or sub phi, sorry. And also, it's a very special property of the Kerr spacetime that it possesses a killing tensor, which is the higher form version of a killing vector. And by contracting the photon momentum with the killing tensor, we get another conserved quantity called the Carter integral. And so the photon trajectory is determined by its initial position plus these three conserved quantities: energy, angular momentum along the phi axis, the Carter integral Q, and signs plus or minus r and plus or minus theta that specify its initial direction of motion. Now, the energy on the null trajectory doesn't actually change the geometry of the trajectory through space-time. Energy is like frequency or color, and so red or blue photons aren't going to be moving through space-time in a different way. So we usually, the energy kind of washes out, and we usually rescale the angular momentum and the Carter constant by the energy. And so what kind of takes the place of the energy as a meaningful conserved quantity on photon geodesics and Kerr is this constant called the Penrose-Walker constant, which is constructed out of the photon's momentum and polarization. And it's a complex constant, which is usually written kappa 1, it's denoted kappa, and it's written kappa 1 plus I kappa 2 to just emphasize that it's complex. And it's a theorem of Walker and Penrose that this constant is conserved on the photon's path. And the existence of this constant, which is ultimately, again, due to the existence of a killing tensor, or for the same reasons, this constant exists for the same reasons as the killing tensor in Kerr. And it's extremely powerful because it says if you know the Penrose-Walker constant and you know the photon's momentum somewhere, you can immediately solve for the polarization without having to do any solution of the parallel transport equation. So as an example of this, we can immediately solve for the polarization on the screen given a Penrose-Walker constant. So as a reminder, we have these Bardeen screen coordinates. This is on our image. And so if we know the position in alpha beta at which a photon arrives, we'll know its arrival momentum. And then if we know the Penrose-Walker constant, we can immediately write down the polarization. And it takes this simple form. This is the longest equation that you'll see in the talk, which involves beta. So the polarization has components, F alpha and F beta, and it involves beta, the arrival position, alpha, which is part of this mu is equal to negative alpha plus a sine theta. And the Penrose-Walker constant, kappa 2 and kappa 1, as well as the black hole's spin, a times the sine of the observer angle theta naught. So again, if we know the arrival position, alpha and beta, and we know the Penrose-Walker constant, and we know the spin of the black hole and the observer angle, then we can immediately see the polarization at a point on the screen. And the fact that the spin appears in this polarization formula is what we can use to extract the spin from looking at the polarization of different subrings. Okay, and another important part of polarization in images is that it will depend on the even and odd parity of n. And the easiest way to see this is by imagining looking at the black hole down the spin axis. If we have a photon that executes n half orbits that arrives at the observer, and then we think about a photon that executes n plus 1 half orbits, we'll see it should have a initial momentum that's oppositely directed relative to the spin axis. And it's only the n and n plus 2 subrings that will have the same initial momentum relative to the spin axis. And yeah, this just has what I said already. Good. And so if we have isotropic emission, the intensity won't depend on the direction of emission, and so we can make a direct comparison between the n and the n plus 1 subrings. However, if we're thinking about polarization, which is fundamentally vector quantity, and it depends, for example, it depends on the, it depends on the cross product of the momentum in the magnetic field. This is a vector quantity, and so we can't compare it between the n and the n plus 1 subrings. It will only be the same for the n and the n plus 2 subrings. Just to get a more physical picture of this, we can imagine some magnetic field configuration around a black hole, which is created when the accretion of gas around the black hole drags the magnetic field line into some geometry. So here it's being drawn into a helix. And if we imagine photons that are emitted in this geometry, we have a photon with n half orbits in green and n plus 1 in purple, and the cross product P cross B will just be different generically for n and n plus 1. And that's what this plot, this sort of cartoon of the photon ring is showing. So here, the different subrings are shown by orange bands that are linearly spaced on a log scale. So they're getting exponentially narrower and closer to the critical curve, which is this black circle. And on top of the subrings are polarization ticks that are in green and purple, and the polarization ticks for the n and the n plus 2, or the subrings that are related by a full orbit, or that are both even or both odd, will be the same, and they'll be different from those that execute n plus 1 and n plus 3 half orbits. So, right, generically we can only relate the polarization of all the even or all of the odd subrings. But there is a way to make a relation between the even and the odd subrings if we make the assumption of equatorial reflection symmetry of the matter on the black hole. And so equatorial reflection symmetry will imply that the polarization encodes spin via the Penrose-Walker constant in a way that I'll explain. But first, I just want to comment that equatorial reflection symmetry is, like axisymmetry and stationarity, a symmetry of the Kerr geometry. And we find that under time averaging, most realistic matter distributions obey equatorial reflection symmetry. So I think it's a good symmetry to assume. And if we assume equatorial reflection symmetry of the matter on the black hole, we find that photons that are emitted in n and n plus 1 half orbits will have Penrose-Walker constants that are complex conjugated relative to each other. And this is because of the flip in the direction between n and n plus 1. And so what this says is that we can, here, I'll go back. Just focusing on this relation, if we know the Penrose-Walker constant for the nth subring, we can immediately find that for the n plus 1 subring. Again, this is in a large n approximation where all the photons are arriving at us at the same point in the critical curve. So here, we can just recall the formula for the polarization on the screen, which is only a function, again, of alpha, beta, and the Penrose-Walker constant plus A times the black hole sine of the observer angle. And so if we know the position, alpha and beta, of the arrival of some photon corresponding to an nth subring, and we know it's Penrose-Walker constant, this immediately lets us solve for the n+1 polarization because it will have the same position and a complex conjugated Penrose-Walker constant. And that means that if we compare the polarization in the n and the n+1 subrings, we can eliminate kappa and just solve for the black hole spin. So if we, in particular, if we take these sums and differences of the polarization in the n and the n+1 subring, and then take ratios of their components, we can solve directly for alpha plus A sine theta O over beta. And alpha and beta will be the position that we know, F plus and F plus alpha and beta will be the measured polarization, and that will allow us to solve for A, the spin times sine of the observer angle. And if we can learn the observer angle from another method, like looking at the orientation of the jet, this could allow us to find the spin. So again, this is a universal prediction in the sense that it doesn't depend on what the value of kappa actually is, which is a complicated, that comes from the magnetic field, and it could in principle be very complicated and different for different black holes. But no matter what it actually is, you can use this method to find the black hole spin, which is encoded in the polarization. All right, so that's the end of what I wanted to cover with these interesting universal features of black holes. And what I want to emphasize now is that it's actually feasible, hopefully, to measure these things with the future extension of the Event Horizon Telescope, which can teach us a lot about fundamental black hole properties. So in this section, I'll cover the answers to the questions of how the EHT takes high-resolution images, which is very cool, what the subring signal looks like, and how much more resolution we might need. So the Event Horizon Telescope uses a technique called very long baseline interferometry, which I'll explain now. Just this is all review, but so one telescope has a resolution that depends on the wavelength that you're observing at and the telescope's diameter, which goes as lambda over d. So bigger telescopes will have higher resolution. In interferometry, it's a technique that uses multiple telescopes to simulate a bigger telescope where the diameter of the telescope is equal to the separation between the telescopes, which is called the baseline b. And so now the resolution will depend on lambda over b, which means that longer baselines, again, have higher resolution. So in principle, this can give you very high resolution, but there's a price, which is that each baseline only samples one Fourier component of the image. And that's like saying if the image were a song, each telescope is only going to sample one note of the song. And so trying to reconstruct an image based on spatial components is like trying to identify a song based on only limited number of notes. And we can do this exercise by trying to identify a song using only limited frequency information. So usually, if this was an in-person talk, I would ask people to raise their hands when they identify the song. But now you can just think to figure out when you identify it. So we'll start with only one note, which corresponds to having one pair of telescopes or two telescopes and one baseline, and then add more information and see what we can learn and when we can identify a song. So let's start playing. Now we're adding, hopefully it's loud enough. Now we're adding more and more stations and more baselines. We're adding more notes on the keyboard. The people would be raising their hands by now. Hopefully, some people might be. And then eventually we'll have full coverage and we can hear the entire song. So one of the things you might have noticed during this demonstration is that even without full coverage, you could still identify the song using partial coverage of the keyboard. And you might actually be better at doing this if you had heard the song before, for example. And it's a similar thing in the Event Horizon Telescope. They don't need all of the information in spatial frequency space to reconstruct the image. They can use the partial information plus some rough idea of what the image will look like to do the reconstruction of the image from the frequency components. Sorry, there's a truck outside. Hopefully it's not too loud. Right, and so that's what the Event Horizon Telescope does. I will set the image reconstruction techniques aside for now and just say the Event Horizon Telescope uses telescopes that have baselines covering the entire Earth to simulate an Earth-sized dish. And the EHT is observing at 230 gigahertz, which corresponds to an observing wavelength of 1.3 millimeters. And with an Earth-sized dish, you get a telescope that has a resolution of about 20 micro arc seconds. An arc second is 1/3600th of a second. And this is like the resolution of being able to read a newspaper on the surface of the moon. And it's just enough resolution so that we can observe the shadow of M87 star, which has a width of about 50 micro arc seconds on the sky. Of course, once you see the subrings, we'll need higher resolution. We'll go into that. But one other question you might have is that with only 5 sites, the EHT only used 5 sites in 2017 to make this image, which corresponds to only hearing about 10 nodes. And how can that be enough information to reconstruct the image? And there's one other very important part of the EHT that it uses to get more information, which is that it makes the Earth part of the instrument. And so as the Earth rotates, the baseline, as seen from the black hole, will change in orientation and in length. We can imagine putting this baseline on some plot in frequency space, and then I have to sync these up. As the Earth turns, baseline will sweep out different orientations and different points in frequency space in north, south, and east-west frequency, and thus cover more of, they call these components U and V. So we'll cover more of this UV frequency plane, which will give us a better way, more information to reconstruct the image. And just as an illustration of what the data would look like with different number of sites, if we only have one baseline, which is 2 sites, you can't see anything. And as you add sites, you add baselines, and you're better able to reconstruct the image. So eventually we get to 5 sites and 10 baselines, and we can reconstruct the image pretty well. So image reconstruction deserves many entire talks in its own right. But what's beautiful also about the photon ring is that you don't need to do any image reconstruction to see the universal features of the subrings, because they're well separated in Fourier space, essentially because they have different sizes or different spatial frequencies. So am I doing on time? Okay,
you have
great.
about 7 minutes, Mina.
Yeah. Okay, yeah, so the subrings are well separated in Fourier space. They have different sizes, and to see what they'll look like in the interferometric data, which is called the interferometric visibility, but it just means the Fourier transform. We can think about what the Fourier transform of a ring looks like. It looks like a delta function, and it will decay with baseline length or with frequency as an inverse square. So baselines that are able to see a ring will see something that decays as an inverse square. But once a baseline becomes long enough to have high enough resolution to resolve the width, to say, oh, this isn't a delta function, this is actually something with a finite width, the signal will start to decay exponentially. And this means that the signal that corresponds to a certain subring will dominate in Fourier space at baselines that are long enough to resolve the diameter of the subring, but not its width. And this is what's being shown on this plot on the right. So the n=1, the signal from the n=1 subring will dominate in Fourier space while it has this inverse square decay. I really hope there's not too much feedback from this truck that's outside my house. It's, I guess, garbage day in Cambridge.
You're coming through clearly. It's okay, Mina.
Okay, yeah. And then the signal will start to decay exponentially once the baseline gets long enough to resolve the width of the subring. And then the signal from the n equals 2 subring will start to dominate because it's still decaying as an inverse square, because the baselines still aren't long enough to resolve the fact that the n equals 2 subring has thickness. Remember, the n equals 2 subring is exponentially narrow compared to the n equals 1 subring. So these will give well-separated signals in different baselines in Fourier space. The current EHT doesn't have baselines that are long enough to resolve the subrings higher than n equals 0. But if we have telescopes that are at baselines of a distance of a geosynchronous orbit, or at the moon, or at the Lagrange point L2, we'll be able to resolve the different subrings and then make a comparison between potentially one even and one odd subring, like n equals 2 and 3, and extract the universal features of the demagnification and the spin in the polarization. And so just like the demagnification and the spin appear in the image, they'll appear in the Fourier coefficients, and we can extract them using relation between the Fourier coefficients of different subrings. All right, so that's it. I think, great. I'll summarize what I've talked about. The images of black holes have a series of exponentially narrow subrings that exhibit this self-scaling symmetry, and they have a polarization that encodes the black hole spin. The subrings in their polarization pattern are universal effects of GR in the sense that we expect to see them for any black hole, no matter what type of magnetic field or accretion disk it's surrounded by. And we actually hope to measure these things with a future extension of the Event Horizon Telescope, or the next generation Event Horizon Telescope, which is the next iteration of the EHT, to space, which can provide a precise test of general relativity in the strong field regime that hasn't been done before, and teach us about fundamental physics, as well as allow us to make precise observations of these parameters, including spin. And there's also lots of other work in different directions, including time delay of the different images for different subrings, potential other symmetries and correlations, and it's very exciting and ongoing work with the EHT. So I'll stop there and answer any questions. Thanks.
Thanks so much, Mina. It was a wonderful talk. So as usual, if you have questions, please use the hand-raising tool in the participants window, and I'll try to call you in order. Again, you can use the chat window if you'd prefer to have me read the question for you. I see a hand right now from Eric. Eric, go ahead.
Thank you, Mina. That was a marvelous talk. I'm curious, as a kind of a natural follow-up from my talk, and it's something I also know that Ramesh is very interested in. Is there anything in the subring structure that we can use to distinguish whether what we're seeing is a black hole or a naked singularity?
I think right now I haven't worked directly on that, and I think I haven't, so I haven't, I don't know what the subring structure would be of a naked singularity, but presumably, so the answer to your question is I haven't worked on that and I'm not sure, but do you know if this naked singularity would give this any kind of bound orbits or subring structure, because the existence of these photon orbits relies on that?
Well, most of what I know about this comes from conversations with Ramesh, and what he tells me is that at the level of resolution we have, we would expect essentially to see almost exactly the same thing that we see right now with the rough circular image. But I don't know anything about finer detail than that. So I was hoping you might know.
No, that's a great question.
This is Ramesh Narayan, right?
Yeah.
Yes.
Yeah. Right.
Yeah, and I'll ask Ramesh about it. Yeah, I talk to him regularly. Yeah. I think at this level of resolution, I mean, we haven't seen the subrings yet, so we're hoping to see them. So right now, I think we can't tell, but that's a great question. Yeah.
Great, thanks, Eric. I have a question here from Carlo in the chat. If it's all right, Carlo, if I read this question.
Sure.
But you just asked, what makes one side of the observed image more bright?
Okay, so this comes from the dot. So if you imagine looking at the black hole and you curl your fingers using the right-hand rule for where the brightness enhancement is, you'll see that your thumb is pointing sort of left and into the page. And this is the direction of the spin of M87. And so the brightness enhancement comes from Doppler boosting of matter that's rotating along with the spin toward us. Does that make sense?
Yes, entirely. Yeah.
Okay.
So it's where the accretion disk is moving toward us, a little bit more toward us than elsewhere.
Yeah.
Thank you.
If you want to just indicate maybe with your stylus where the axis of rotation is in this picture.
So it sort of here. Yeah.
Yeah. Thank you. Thank you. I had debates about that. This makes complete sense to me.
And I guess it's into the page, so it'd be like a little X or something.
It's an angle, right? It's at the theta 0 angle from the
page. So we think theta O is 163. So into the, if we're looking down, it would be 163. You know, if the theta axis is measured from my finger pointing down, it would be at 163 degrees into the page.
Okay.
Yeah, 17 degrees off axis. Yeah.
Great. Yeah. The next hand I have is from Julius.
Thanks, Mina. That was beautiful. I wanted to ask you whether you know if we could extract some precise predictions from the structure of subrings or their occurrence from modified gravity theories. And so whether we could try to distinguish between GR and alternatives to GR using these sorts of structures.
Yeah, so like I mentioned, I'm not sure about naked singularities, but there are lots of modifications to GR that will predict different, you know, have extra fields or stuff like that, that will predict a different subring shape and size. And so by confirming that the subrings match this, what's predicted from GR, we can confirm it and then exclude other theories in that way. Now, of course, it doesn't say that if there's some other theory that predicts the exact same shape and size of the foot of the shadow, we can't rule that out, but we could rule out ones that make different predictions. Yeah.
Can I have a follow-up on that? Do you know if there's a particular modification of gravity that would give us the same predictions for, let's say, up to n = 3 or 4 or something like that?
There's not that I know of. Yeah. But I haven't looked a huge amount into, I haven't looked exhaustively into other predictions at all. So.
Yeah. Cool. Thank you.
Eric has a finger on that question. Eric?
Because the photon is essentially, all the photons are essentially test matter, and the accretion is basically test matter. You would expect that any alternative gravity theory that depends on powers of the Riemann curvature, of Ricci curvature, should give exactly the same answer.
Yeah, I'll think about that. Yeah. But I guess the things that I've seen have been like sort of adding extra, adding other modifications like additional fields that would give like frequency dependent effects of this, et cetera. And those would predict different shapes and sizes.
So I had a quick question. Mina, could you talk a little bit about why we took a picture of this black hole and not, say, the supermassive black hole at the center of our own galaxy? Like relative sizes maybe on the sky and maybe other considerations that went into that decision?
Yeah, so the relative size of M87 on the sky is about, they're actually both roughly the same size. They're roughly 50 microarc seconds. Sagittarius A star is actually a little bigger. So we'd only need like 50 microarc second resolution as opposed to 20 microarc second resolution for M87. But Sagittarius A star has an image that's changing over time much more quickly. The orbital period of stuff in Sagittarius A star is like minutes, as opposed to M87, which is days. And so if we're trying to get enough data as the Earth rotates, over many days, we want to do a time averaging that makes sense. It's easier to see M87. And to get accurate pictures of Sagittarius A star, which is moving on a faster time scale, we'll need higher resolution, and that's being actively worked on. But Sagittarius A star and M87 are the two primary black holes that are close enough to see reasonably with an Earth-sized dish. And I don't know, I should know it, but I don't have on top of my head the size of the next biggest one. Yeah.
Thanks, Mina. So I don't see any more questions. We finished a little bit early with the question period, so we can take an 8-minute break. So I want to thank Mina again. Thank you so much for a wonderful talk. And people can take a few minutes for a break. And during that time, Lydia, you can get your slides ready to go. I'll stop the recording.